What are ceramics and why do they matter? Ceramics are inorganic, non-metallic solids made of metal or non-metal compounds that are often strong yet brittle. Some of the most common examples of ceramics are glass, pottery, concrete, etc. Ceramics are important to us because they are used in everyday life for things like the windows in our houses, or the bridges that we drive over, or the screens of our phones that we're on 6 hours a day. They're even in the pencil lead that we use to write with. It is important that we understand how to measure the strength of ceramics to help avoid failure in real-world situations, whether these are minor or major failures. Ceramic failures can be catastrophic or they can be minor inconveniences. Either way, they happen every day. Regardless, it is important that proper measures are taken to prevent these failures, especially the big ones. A couple of examples of major failures are the Morandi Bridge in Italy, 2018. After an independent investigation, it had been determined that cracks in the concrete allowed water and salt air to seep inside and corrode the steel cables. This caused the cables to give out and eventually led to the bridge collapsing. Had there been proper care taken to prevent cracking, or even inspection to see the cracking before it got too bad, they may have been able to fix the bridge before it collapsed. Another example is the pedestrian bridge collapse at Florida International University, 2018. While the bridge had been under construction, part of the bridge gave out, and it was later determined that errors in the load capacity calculations were the reason for the collapse. There are even many everyday instances of failures that we experience often, such as your phone screen cracking after being dropped, or a mug shattering after it slips out of your hands.
Oakland, drivers hurried home to catch the opening pitch. They pulled onto the Cypress Street Viaduct, a 2-deck, multi-lane freeway hoping to beat the rush hour traffic. The earthquake struck at 5:05 p.m., about 30 minutes before the opening pitch, and the ground shook beneath the bridge, causing the catastrophic collapse of the Cypress Street Viaduct. The viaduct's top deck was reserved for southbound traffic into Oakland, while the lower deck was used for northbound traffic towards the highway in San Francisco. 2 support columns on either side held some bridge sections in place. Others relied on a single support column.
Ceramics are known to be brittle materials and are extremely sensitive to defects. This means that ceramics will not undergo any kind of significant deformation or stretching before they break, and that their fractures will always originate from some sort of flaw in the sample's surface or body. The flaw can be anything from a microcrack to a visible scratch and is essentially just a weak point in the sample's structure. The sample fractures when one such flaw is placed under enough stress to essentially extend, causing a break in the material. This point is labeled as the flaw origin and is surrounded by what's known as the mirror region, which tends to be quite smooth and reflective, like a mirror, hence the name. This is then followed by the mist region and finally the hackle region, which is made up of these ridge-like lines which lead to crack branching. These hackle marks also indicate the direction of crack propagation. In other words, this region shows the extension or development of that original flaw and its direction. The high sensitivity to defects found in ceramics actually leads to scattered fracture stress measurements, since the amount of stress needed to break a sample is almost entirely dependent on the defects present in that particular sample. So you can see quite significant differences between the fracture stress measurements of 2 samples of the same exact material and dimensions, meaning that using this data can be a little tricky. We'll explain how to properly manage all of that a bit later. Instead, right now we'll jump into the lab activity, starting with the appropriate safety measures.
For the safety portion of this lab, you must be wearing safety goggles to protect your eyes from any particles that may break during the procedure. You have to wear these Kimtex gloves so your hands are protected. You're wearing closed-toed shoes and long pants, and if you have long hair, make sure it is tied and put back so that it doesn't interfere with the procedure when you are doing it.
Before running the tensile strength test, we measured and recorded the diameter of the glass rod using a caliper.
Here is a clip of bad lab practices. Don't place your glass rod on the lower supports of the bend fixture and bring down the upper support so fast you break the rod and have no time for data collection. For best practice, we suggest placing the glass rod in between the bend fixtures and adjusting the upper fixture up so the glass rod can sit comfortably on the support points. Then you can start your test on the computer. Here is a shot of a successful 3-point bend test. After the data collection is over, your software will show you the real-time plot of the rod enduring stress as the upper fixture was lowered by the machine. You can easily see the fracture point of the glass. You will head over to ARMS 2130 or the Optical and Mechanical Testing Lab to view the fractured surface of the glass rods. First, you'll pick a colored clay that you think will help produce a nice image, and then you will form an oval stand so that your fractured rod can stand upright if you stick it in the clay. The fractured surface should be visible from the top down. You'll place the clay stand under the optical stereological microscope and play around with the lighting and the adjustment dial until you have a clear image you're satisfied with. Here is our image under the microscope. When we obtain the image of our fracture under the microscope, we can do a failure analysis that looks into the location, type, and source of the flaw in the glass rod that creates the crack. This is called a fractographic study. In our image, we can tell where the site of nucleation or where the flaw spreads by realizing where the cracks all line up or converge to a point. Distinctive features can also be noted on the surface of the fracture, such as the mirror region, hackle region, or mist region. By comparing our image with the images of known specimens, we can see our image resembles a high fracture strength surface because of the similar distinctive features such as the origin of fracture and hackle region. The other image has no distinctive feature that is comparable to ours. After analyzing the picture and collecting the mirror radius from the nucleation point to the end of the mirror region, we can understand the stress level the fracture occurred at, as seen by this proportionality statement.
This is a setup of a 3-point bend test. It's supported by the loading anvil and supporting anvils. The length we need for calculating the flexural stress is the distance between the two supporting anvils, which can be measured using a ruler. The radius of the glass rod is used by the caliper method, as seen in the previous segment video. The loading anvil breaks the sample, and the bottom portion of the sample feels tension due to the bending stress and its location with the center of mass, which is the centroid, which makes up the neutral axis. And so the tension is the greatest with the maximum moment, which is located at a distance in the middle of the beam. And so we plot the flexural stress values to create a histogram of the distribution to calculate the Weibull modulus using the Weibull statistics.
Because the fracture strength of ceramics such as glass is so heavily based on the flaws and defects present, we have to use something called Weibull statistics to get a better idea of how they fracture. To do this, we first run a number of 3-point tests on a material, then we rank these tests from least fracture strength to greatest. Once we have them in order, we use the first equation to get an idea of the probability of fracture at any given stress value. The probability of fracture being equal to the rank of the chosen sample divided by the total number of samples plus 1. You can then take that probability of fracture and put it into the equation natural log of 1 divided by 1 minus probability of fracture and set that as your y value, and set the x value of a graph to be the natural log of stress. And it's the same way as the figure. From this figure, you will find the slope of the line. The slope is something known as the Weibull modulus, which is used to determine the consistency of a material's fracture strength, with lower values indicating lower consistency. Ceramics will typically have a Weibull modulus ranging from 3 to 5, while metals and alloys can typically be upwards of 90. It makes sense that metals would have much higher Weibull modulus because they are not very susceptible to flaws and defects within the material because of their metallic bonding versus ceramics, which have primarily covalent and ionic bonds. Ceramics are something we see a lot in everyday life, such as mirrors or bridges, and their fracture strength is something that is very important to know, since using a material with too low fracture strength can cause catastrophic failure when too much stress is applied, such as a bridge collapsing. This makes it very important to get an idea of the probability of fracture at any given stress value, which is why we run so many 3-point tests and use Weibull statistics to make sure we get the right ceramic for any given situation.